Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to the course entitled Advanced Transition Metal Organometallic Chemistry. In this course, we have been looking at the utility of transition metal complexes, particularly from the catalytic viewpoint, and we had seen that how these transition metal complexes, some of them, some important ones, have broken the barriers or confines of the laboratory and have gone beyond the reaching the utility space and gone on to become blockbuster catalyst in terms of producing important chemicals or compounds in a catalytic fashion in large scale up processes. So, from that perspective, what we had been looking at is the success of various organometallic catalysts, particularly in their application utility in large scale processes. Now, one of the main factors which we found common for most of the successful catalysts is the fact that these catalysts carry out the reactions under mild conditions and also in high turnover and throughput. So, this high efficacy of these catalysts is what make them so special for their application or utility in large scale industrial processes. So, in that perspective, we have been discussing about various catalytic reactions, particularly the palladium mediated CC coupling and cross coupling reactions. We have also looked at the nickel mediated hydrocyanation reactions, and then we have been looking at these carbon heteroatom bond forming reactions, and in that context we have looked at CN bond forming reactions, particularly from arene amination reactions and hydroamination reactions in the last class, and today we are going to move on from this CN bond forming reaction to another important Cb or carbon boron bond forming reaction when we take up this topic of hydroboration reaction. Now, boron hydrides have been useful reagent ever since for carrying out many important reactions in organic synthesis and has been known to chemists for long, and from that perspective these hydroboration reactions, which is an addition reactions to olefin, is of prime importance, and also the fact the catalytic hydroboration reaction being able to perform using organometallic catalyst is also an important discovery with regard to this hydroboration reaction. So, one can say that hydroboration reaction, the catalyst controls the cumuloselectivity of catechol borane. Wilkinson's catalyst controls the chemoselectivity of hydroboration of catechol borane. So, let us sort of see the influence of the catalyst and how this is affected by this hydroboration reaction for these two reagent. BH plus this olefin ketone compound when uncatalyzed this BH reduces the carbonyl compound and leaves the olefin intact to give this as the major product. This as the main product. However, when Wilkinson's catalyst is used, whole 3 P rhodium chloride at 0.5 mole percent leaves this carbonyl intact and hydroboration happens on the olefinic end to produce this compound. So, what one can see that the chemoselectivity of hydroboration of catechol borane can be controlled when the reaction is performed in absence of the catalyst versus the reaction performed in presence of the catalyst. And as a possible mechanism for this hydroboration reaction, as L3 chloride would loses an L to give L2 rhodium chloride, L equals P pH3. This would react with R2BH, and this step is the oxidative addition step that one is familiar with. To give the corresponding rhodium 3 compound or H B R2 chloride L. Now, these then undergoes a coordination from the olefin, and this step is called coordination. To give the corresponding olefin coordinate complex with the elimination of L, one of the L is lost, and one can get rhodium L pH Cl H B R2 and that then undergoes this rhodium hydride, then undergoes insertion into this olefinic bond to give the rhodium alkyl species of the type R, and then in presence of the ligand L, which comes out over here, to give Cl L L P H B R 2. So, this is the insertion step, and if one were to look at how this insertion step happened, the hydride is inserted from the hydride attack on the olefin happens from the exoside outside, making it converting it into a methyl group, and rhodium is bound to the inner carbon over here. So, in this second, so this kind of addition is is a Markovnikov kind of addition, and then finally, so this hydroboration on this olefin when it is catalyzed by a catalyst, then the addition is a Markovnikov type addition, whereas hydroboration of olefin in absence of any catalyst goes by the anti-Markovnikov kind of addition. So, once this is formed, then it undergoes reductive elimination to give the desired anti-Markovnikov product, which is P H B R 2, and this process is called reductive elimination. So, what we see that hydroboration reaction, it's indeed is a 4 elementary step process, in which the first one is oxidative addition, second one is coordination, the third step is insertion, and the fourth step again is reductive elimination. One should note that this insertion happens in a Markovnikov fashion, and that the hydride moiety from the rhodium attacks the olefin from the on the outside carbon, converting it to a methyl group, and the inner secondary carbon is bound to the metal, and followed by reductive elimination to give this Markovnikov addition. So, this is an important reaction, as we see that this hydroboration reaction to olefins, when catalyzed by Wilkinson's catalyst, then the reaction happens in a Markovnikov fashion, whereas the product obtained in absence of the catalyst is anti-Markovnikov addition product. So, this is kind of interesting that the Wilkinson's catalyst produces Markovnikov product, whereas anti-Markovnikov product is obtained in absence of catalyst. whereas anti-Markovnikov product is obtained in absence of catalyst. So, the hydroboration reaction has also been extended for asymmetric for organic synthesis in an enantiomeric fashion, and we are going to take a look at one such example in which the reaction is done in a highly enantioselective fashion. So, this is examples of asymmetric hydroboration reaction. And the beautiful example is given by R2 R1 presence of this chiral catalyst L star rhodium cation and catechol borane, which is and L star is binap, giving the following two compound R1 R2 B and the opposite enantiomer R1 B which upon oxidation DATION gives catechol and the corresponding alcohol R2 R1 OH plus R1 R2 OH. So, the even though the best enantioselectivity is achieved using this bi-non ligand, the best enantioselectivity is achieved by incorporation of chiral by NAP ligand, though EE is less. So, what one see is that this hydroboration reaction can also be extended to carry out addition of BH to olefin in a asymmetric fashion, and the best enantioselectivity though have been achieved with binap ligand. However, the E in this still remains less and needs to be optimized further. So, here is another interesting addition reaction that we had spoken about, and this is this hydroboration reaction. Two things which comes in our mind, that chemoselectivity of the hydroboration reaction can be altered when by using a catalyst. When it is uncatalyzed, it was reducing the ketone, whereas in a substrate containing the ketone and the olefinic bond, and when catalyzed with Wilkinson's catalyst, it was reducing the olefin. Furthermore, there is a sharp distinction between this hydroboration reaction of olefin when catalyzed as opposed to when uncatalyzed. When catalyzed, this hydroboration reaction in olefin proceeds via Markovnikov addition, whereas when uncatalyzed, this hydroboration reaction of olefin proceeds in an anti-Markovnikov fashion. We have also observed that these hydroboration reaction can also be used to carry out olefin reduction in an asymmetric fashion. However, the enantiomeric excesses obtained for these reaction is still in its infancy and needs further improvement, though the best enantioselectivity has been achieved using this chiral BiNAP ligand. Now, as far as the catalytic cycle of hydroboration reaction is concerned, we have seen that this hydroboration reaction consists of 4 elementary steps. The first one obviously is the oxidative addition, followed by olefin coordination, subsequently word olefin insertion, and then finally reductive elimination. Now, this hydroboration mechanism is quite similar to the nickel catalyzed hydrocyanation reaction we had discussed earlier. There also it had a similar kind of catalytic cycle. However, this hydroboration reaction is startlingly different from various other kind of CC bond forming reaction like palladium mediated cross coupling reaction, which also had 4 elementary steps, but the 2 were same and 2 were different. The 2 steps that were same were oxidative addition, reductive elimination, and the steps which were different were transmetallation and cis trans isomerism in terms of the palladium mediated cross coupling reaction. So, with this we would like to conclude with today's topic of hydroboration, and with this we have looked into various kinds of carbon heteroatom bond forming reaction. The ones that we have looked so far are 2 methods for C-N bond forming reaction and 1 method for C-B bond forming reaction, and we are going to move on to another interesting topic, which is C-Si bond forming reaction in the form of hydrosilylation reaction in the subsequent topic. Now, we have as far as the CC or CN or CB bond forming reaction, we have seen that these bond forming reactions are of 2 approaches or 2 one is simply this metathesis reaction, and the other is just the addition reaction through again to the olefin or alkyne unsaturated compounds. So, hydroboration reaction falls into that category, whereas the other CC cross coupling reactions falls into the category of the metathesis type. Now, as far as utility is concerned, we had seen that hydroboration reaction indeed has a lot of examples in terms of uncatalyzed reactions, which is a routine organoboron hydride reagent used for various forms of reductions of carbonyl moieties or olefins and so on and so forth, and they can also be used using metal catalyzed fashion for carrying out the reduction. And in this particular example today, we had seen how Wilkinson's catalyst was used for reducing the olefinic bond using boron catechol hydride reagent. So, with this I would conclude today's discussion on on hydroboration reaction in general. We had seen how this reaction can be controlled chemoselectively. We have also seen the mechanism of this reaction, and particularly we have observed how this reaction differ from the sense of the traditional CC bond forming reaction, and how does it resemble quite similar to that of the hydrocyanation reactions that we had earlier discussed. We have also looked at the kind of addition that one observes, and what we had noted that in terms of hydroboration of olefin, the Wilkinson's catalyst mediated hydroboration reaction allows the reaction to proceed in a Markovnikov fashion, in which rhodium hydride moiety attacks the olefin from the less ended side, whereas the uncatalyzed hydroboration of olefin proceeds in an anti-Markovnikov fashion, and this is similar to what people learn in their first year freshman organic chemistry course, that hydroboration reaction proceeds in anti-Markovnikov fashion. So, we see the chemoselectivity, the type of addition can be controlled and made different by using different catalysts, and that is where the power of catalysis comes into play. So, with this I am going to conclude today's lecture, and we are going to be taking up another such carbon heteroatom bond forming reaction, and this one is going to be another utility oriented reaction, which is hydrosilylation reaction, in the next class when we meet. I sincerely thank you for patiently being with me and listening to this lecture today, and I look forward to being with you in the next lecture when we take up this topic of hydrosilylation reaction in more detail. Till then, goodbye and thank you.